Hello everyone, this is Vasant, a ninepointer at IIT Bombay from the Department of Civil Engineering. Today we are going to solve a problem on statically indeterminate structures. So this is the problem over here. You can read. See, this is the rigid bar AB. This is the rigid bar. So there will be no deformations. It may deflect like this. Okay, whole body will deflect, right? So there will be no deformations in this bar. So this is basic. So no deformations. Pinned at point B. So this is pin support means it won't resist movement, means it can rotate but it won't move in forward direction or in forward backward and upward downward. Okay, it is resisted in forward horizontal and vertical movement, but it is not resisted in terms of rotation. So the springs are there at A with stiffness constant K1. Springs at D, spring at D has stiffness constant K2 and load P is applied here. So if you apply load P here, this is fixed over here, sorry, pinned over here, you can move like this. So and but there are two supports here in the form of springs. The support is in the form of springs. So I want to say one thing over here. To take length L, A comma B, T. What is the deformation delta? Delta will be P L divided by AE, right? So you can write it as P divided by AE by L, right? So similarly, if you take a spring with constant K and you applied load P, then what is delta? Delta will be is equals to P by K, right? So in similarity, in analogy terms, K is equals to AE by L. So you can replace the spring by a rod with the value of K AE by L, right? So means though both these have similar functions, so you can directly solve like this. So see, it is not resisted in movement, so it can rotate freely. So if you give one rod over here, then it will won't rotate, right? So it will be unstable and it is statically determinate. But you provided two rods, right? Means two springs means two rods, so it is statically indeterminate structure to 1 degree. So you are applying load P here, so it will try to move it downwards. The right part will try to move downward, so that will compress the spring over here, right? It will compress the spring over here. Compression. Here there will be tension, right? Okay. So he given that the angle of rotation, whatever the angle of rotation means, it will rotate, right? So it will rotate like this. So whatever angle of rotation is there, that should be limited to 3 degrees. Okay. So then what is the maximum permissible value of load that you can apply? So let us go. So let us draw the diagram. This is this is K2, K1. So here over there is pin, right? And the load is applied over here B. This is A, B, C, D. Right? So you are trying to compress it, then spring will try to give. See, you are trying to compress this spring. So you are trying to apply load P, some load P1 like this. Then spring will give equal and opposite load, right? So it will try to apply force upwards on the rod. Okay, that will be is equals to K2 del 2. That means K2 x2, right? So this is P and this distance is given as C. This distance is given as B. This distance given as A. So and see, when you apply load like this rod will try to go upwards in left side. So the spring will try to compress it, right? So in left hand side, the force will be K1 x1. So let us draw the deflected shape. This is P. P is applied over here, and here it is K2 x2. Here it is K1 x1. The deflected shape will be something like this. right? Deflected rod shape will be like this. So this will be theta. Theta max, theta is limited to 3 degrees, right? Maximum it can go up to 3 degrees. So this is x2, this will be x1, right? So we can apply equilibrium equation at point B, moment equilibrium equation at point B is equals to 0. Then we will get what we get, k1 x1 a plus k2 x2 b will be is equals to p into c. Okay, because this is c, this is c, this is b, this is a. So this is one equation. Another equation is x2 divided by b will be is equals to x1 divided by a. So then x2 will be is equals to b by a x1. So this is equation 2. So put equation 2 in equation 1. Then you will get k1 x1 a plus k2 x1 b square divided by a, right, is equals to pc, right? So it will give x1 common, you will get k1 a square plus k2 b square divided by a is equals to pc. So then you will get x1 will be is equals to PAC divided by K1 A square plus K2 B square. So this is x1. Then what is the value of x2? So x2 will be x2 is equals to B by A into x1. So x2 will be B by A into x1 is PC into A divided by K1 A square plus K2 B square. So A gets cancelled. That will give us to PBC divided by K1 A square plus K2 B square. This is x2. What is theta? Theta is x2 by b or x1 by a. That will be is equals to PC by K1 A square plus K2 B square, right? They said that is less than or is equals to 3 degrees. So PC divided by K1 A square plus K2 B square, we need to convert 3 degrees into radians. Okay, that will be 3 divided by 180 into pi. So that will be P will be less than or is equals to 3 by 180, 3 pi 180 into K1 A square plus K2 B square divided by C. So P max will be is equals to 5 by 60 into K1 A square plus K2 B square divided by C. Okay. So this is the value of equation for P max. So we already given K1 is equals to 10 kilonewton per meter. K2 is equals to 25 kilonewton. And A is 250. A is 250 mm, right? So 250 mm means 0.25 meter. B is 0.5 meter and C is 0.2 meter. Okay, so substitute these values, we will get P max will be is equals to 1800. Okay. So with this, we end today's lecture. In next lecture, we are going to solve one more last problem on statically indeterminate structures. Until then, take care. Bye bye from 9 point.